Hello, everyone. Welcome to Kotlin Under the Covers? Under the Hood.
Under the Hood.
We've called it many, many names. We'll call it this one right now. We want to look at the way some of the features in Kotlin work. I'm Chet Haase.
And I'm Romain Guy.
And let's do this thing.
Yeah, and we gave this talk before, like a few weeks ago in France. The difference is today we have people from JetBrains in the audience. So we're probably going to say something very stupid, so feel free to yell at us. It's fine.
Yeah, so we'll see if we were actually correct when we wrote the talk. So Kotlin, very awesome language, very cool, lots of interesting features.
You're doing it again. You're taking my slide.
Are you going to go? Why don't you talk?
So Chet has this issue. In the speaker notes right here, it says my name, and he starts talking, and he keeps stealing my slides every time. All right, so Kotlin is awesome. Who's using Kotlin here? All right, so we don't really have to convince you that Kotlin is great, but just in case, it's concise, you have less boilerplate, you get powerful extension libraries. We write our own. There's a bunch of Android X or Jetpack extension libraries for various APIs, platform or not. Fully compatible with the Java programming language, and therefore the Android APIs, which makes it very easy for you to adopt in your application. And it has a lot of modern language features like coroutines. Chet, what are coroutines?
Things.
All right. And it's always evolving.
But some of these magical things in Kotlin really are magical and mysterious. How do those things work, especially since we're compiling down to the same bytecode that runs other languages that don't have these features? So how does that stuff work? So that's the whole point of the talk. Take a look on the inside and see what's going on. We're going to take a look at two different things right now. Today we're going to look at how these things work, and we're also going to show you some tools to use to get this information, basically the tools that we use to discover this stuff. We're not going to do it in that order. We're going to do it in this order instead. So first we'll talk about the tools, and then we'll talk about the features. So, tools.
All right. So there are two tools you can use. The first one is looking at the Kotlin Bytecode. There's a special tool for that in IntelliJ and Android Studio. And the second one, part of the same tool, is you can convert the bytecode back to the Java programming language, which sometimes is very helpful to understand what's going on so you don't have to decipher bytecode yourself. Finally, the memory profiler, so not about the bytecode itself, but sometimes some of those language features may create allocations, which may or may not matter depending on what you're doing, what kind of code you're writing. But it's a very useful tool to know about in general, not just in the context of this talk. So here's an example. Primitive types are handled a little bit differently. So in Kotlin, when you say this, var I0 equals 5, obviously you're declaring an int. So capital I int, it's non-nullable, so it cannot be null. And it's equivalent to the lowercase int in the Java programming language, so it is still a primitive type. Now, if you specify the type yourself, same thing, it's an int, it's a primitive type in the Java programming language. But if you declare it as nullable, the only way we can handle that with the current runtimes is that it has to become the int question mark type in Kotlin, which becomes the capital I integer type in the Java programming language. And suddenly it's not a primitive type anymore, it's a full-blown object. And this can have consequences.
So how do we find out stuff like this? Well, as he said, one of the ways that we can do that is by looking at bytecode, so let's look at some now. That's pretty self-explanatory, so let's move on to something else. So in IntelliJ, there are different ways to look at bytecode, but fortunately we have tools integrated directly into Android Studio, into the IDE. If you go up in the menu, you can say, yeah, show me that bytecode, and then you get this viewer over here. So if you look carefully in the editor on the left, you'll see that the cursor is on a particular line of code, and then it highlights the equivalent bytecode on the right to show you what's going on. Some of the information in the bytecode, it gets a little noisy in there. There's metadata to tell you what line that's associated with, a little extra information, but there's a couple of instructions in particular which are the actual bytecode instructions. So for the stuff, oh yeah, and then there's another way of doing this. On the command line, you can use Java P instead, and that'll spit out a file that you can take a look at, nicely formatted bytecode. It's a different way to do it that's not integrated into the IDE. So for the code that we were looking at before, you have this var I0. We haven't told it it's going to use type inference, but it's set to be this integer value. So what's going on? We have a little bit of metadata about the line numbers, and then it says byte push of the value of 25. So it's going to take that value of 25, extend it to an integer, push it onto the stack. Then it's going to pull it back off the stack, and it's going to store an integer into the first variable. So integer store, and then we go on the second line. We're not using type inference. We've actually said, no, we want you to be an int. We're going to assign you the value of 78. Same thing happens. We're going to push a 78 extended to an integer onto the stack. We're going to pull that off, store it into the second integer variable. And then for the third case, where we have this nullable type, we've got I2 that's going to be a nullable int of a value of 14. First step is going to be the same. We're going to push byte extended as integer onto the stack, but then we're going to call a method. We're going to call integer.valueOf, which looks like this. It takes in an int, a primitive int type, and it returns an integer. So in the middle of that, it's going to box it into an integer type, creating that object on the fly, and then return the integer type. And then instead of storing an integer into a variable, it's going to store a reference to the object that we've created. So if you don't enjoy reading bytecode, it's really not that complicated.
You're doing it again. It
What's
says
that?
my name on the speaker notes.
That's why I was introducing you.
Right,
Romain is
go
going to
on.
tell you what to do.
Keep going, you started it.
So if you don't want to read all of that bytecode, it's actually pretty straightforward. There's some simple reference docs out there that you can take a look at. You're pushing, you're popping, you're setting. But if you don't want to deal with that, there is an easier way, especially a more concise way to see what's actually going on. And for that, you would use the Bytecode Decompiler.
No, keep going, that's fine.
You want me to keep?
No,
Okay.
keep going.
All right, rest of the presentation is mine. Here we go.
I'll be over there.
What's that?
I'll be over there.
All right, so let's say you've got this code. Could you go a little bit further, actually? So you've got this code. You have the bytecode representation over there, and if you look at the top of that window, you've got this button that says decompile. So you click on that thing, and then in your editor window, you'll be shown some Java programming language code that looks more like this. Right? So you got the bytecode fairly verbose, all the things going on. You know, each of the lines of Kotlin code may expand to several lines of bytecode along with the metadata, or you can see this fairly terse Java code instead. You see basically straightforward things going on there. You have some int values, you have some integer values that got auto-boxed, and then we're printing out the values there. Just like that. You want to talk about the memory profiler? Go ahead.
It says your name.
It does.
Okay, so
I'm going to talk about the memory profiler there. The third approach that we have using the tools to find out what's going on is to actually see what's going on with allocations and collections in the system. So one of my favorite tools when I joined the team and for many years after that was, oh, is this proof?
I'm going to tweet that.
Allocation Tracker. Allocation Tracker was a tool that you would run in DDMS, and you would start it at some point in time, and you would use the app for a while, and then you would stop it, and it would say, here are all the objects that were allocated on the fly, and then you could click on any of those instances, and it would show you the call stack. Really powerful, really useful. Wasn't integrated in with any of the rest of the tools, so kind of a pain to get to. A lot of people didn't even know it was there because actually finding it was a little bit tricky. So now we have memory profiling directly integrated into the ID with the rest of the profilers that have come online in Studio in the last few years. So this also allows you to track memory usage over time. You can see how big the heap is at any given time. You can see when garbage collections happen and what happened because of those. And you can catch leaks, which is really powerful. This is another thing that, yes, we allowed you to do it on Android, but oh man, did we require you to jump through a lot of hoops? A lot of heaps. You would, dump a heap and you would transcode that into a different format, and you would use some external tool and then walk through this amazingly complex set of information. Now all of that stuff is integrated directly into the ID. And after all of this, it allows you to track allocations, and that's what we care about today. So I wrote this code all by myself. Really simple thing. We've got this nullable int value. You've got a tight loop in there in the method. We're going 0 to 10,000. So 10,001 times it's going to whip through the loop, and it's going to set. We know that that's going to end up being a capital I integer value set from the primitive I loop value that we've got. So we can click on this in the lower left of the IDE. You've got this little toolbar of little tools you can run. If you click on the profiler, you'll get something that looks like this. It shows you all the profilers that we currently offer. You've got CPU, you've got the memory that we'll look into, you've got networking, and you've got battery power usage. So if you click on the memory one, it expands to take over the whole screen there, and you can see heap usage over time. Now what we really care about here is what happened there. Right? I don't care when it's not changing. What I care is what caused it to actually bump up allocations and heap usage, and why was that? So you can drag the cursor along there, you can select this window of time to see what's going on, and just like allocation tracker, you can see all of the things that were allocated down below. And you can see that, in fact, there are a bunch of capital I integers that got allocated. In fact, there are exactly 9,873, which is weird. We're in a loop going through 10,001 times. Why do we not have 10,001 allocations going on? So there's the loop. And that, for some reason, didn't equal 10,001 allocations, and it's because of the value of, more particularly because of this caching logic that we have. When the runtime starts up, it knows that most applications are going to need some integer values, and so it caches values from negative 128 up to 127, puts them in a cache, and now when anybody asks for a value for one of those, it's just going to return that. It's already been created as an integer. It's not being boxed and allocated on the fly, which means the only values that are going to be allocated are outside of that region, which turns out 10,001 minus 128 is going to be 9,873. Has nothing to do with this talk. I thought it was interesting. So the one that we care about are the capital I integer allocations. So we're going to click on that, and that brings up another window that shows each of those individual allocations, when they happen and what was going on. We can click on one of those, and just like allocation tracker, it pops up the call stack. And from that, we determined that, in fact, that was being allocated because of the boxing operation that was happening in that tight loop.
Let's talk about language features. I appreciate this. Thank you for the cheers, but maybe wait until the end.
Do you mind if I take this one?
Yeah, I do, actually. I can just leave if you want. Anyway, enums, your favorite topic. So please use enums, but we're going to talk about them anyway. So here's an enum I wrote, all by myself as well, called blend mode. We have some values. It doesn't really matter what they are. And here's how I'm using the enum. I'm using a when statement, effectively the equivalent of a switch in the Java programming language. And for every value of the enum, I call a function. That doesn't really matter what we do. What's interesting is what happens when we look at the generated bytecode. So here's what it looks like. The first thing it does is called this, there's this get static opcode. It accesses a int array, so that's the square bracket with the capital I at the end. So it's a field in a class called blending kt $when mappings $enum switch mapping $0. I never wrote a class called this in my code, but there it is. And then what's interesting is after it gets this array, it invokes the ordinal method on the enum value itself, and then it does an IA load. So IA load takes the output of the ordinal method call, and then uses that as an index in the array that we just fetched. So, and finally, it does the actual switch. So it doesn't switch on the enum value itself. It first goes through another array, an intermediate array. And we're going to look at what this array looks like. And then that's our code. So here's what the code, what the generic code looks like. So what is interesting here is that this is not specific to Kotlin. The Java programming language compiler will also do the same thing. But it's still interesting to look at it. So the code that gets generated is this. There's this special mapping class that contains an array that has the same length as the number of enum values that you have in the enum class that you declared. And then in the static initialization code, this array is populated with the values of the enums and some special constants generated by the compiler. So what happens if we create another method in our code that does another when on the enum? So we do a when in the same order. We switch over all the values of the enum. If we go back to the generated class, we can see there's a second array that was generated. And it's also populated with enum values and some magic constants by the compiler. And actually, you can see that those two arrays are exactly the same. They have the same length, and they contain exactly the same mappings. But if we use the enum once again in a when, and this time we declare the enum values in a different order, and we look at the generate code, we have a third array as expected, also the same length, but the mappings are different. I believe the reason the compilers do this is that if you change the enum, the code that was compiled before with the old version of the enum will still work, so they need this indirection. But what becomes interesting is obviously most of the time you will never need to care about this. If you have a lot of whens on enums in performance critical code, you're going to have extra code that gets initialized, that runs at initialization time, and you have this extra hop in memory. But most of the time, you don't need to care about this. Use enums.
All right, let's talk about laziness. I know a lot about this. It's a very common pattern in software to say, I may need to allocate this thing, but it's going to cause a lot of work, and maybe I don't want those allocations and the background work to happen to do that because maybe the code won't need it. So we'll do it lazily. We'll do it sometime later. Right, so manual approach looks like this. So caveat, really stupid example. Nobody should ever do this just to avoid allocating an int, no matter how it's implemented under the hood.
It is a very stupid example.
It is a very stupid example. There is a very real example that is almost as stupid, which is code that we actually saw, which did lazy allocation for a rect object, which is just 4 times less stupid than this, right? So allocating 4 integers, but for some reason they want us to do it lazily because why allocate if you don't need to, right? So bear with me. So we have this int. We're going to set it equal to 573, but maybe nobody's going to need this, so we're going to make it lazy instead. So we're going to have a private member variable that's nullable. Now, part of the problem here is we know from the earlier example is, well, now we have something that could have been a primitive, but now all of a sudden we've made it an object type instead just because we want to set it to null. But anyway, you've got this private member variable, and then you have the actual thing that they're going to access, and you say, okay, when they actually call the getter, we'll see if it's null, and that's the trigger to say, okay, now actually set the value to this thing and return the value, and you're done. Next time they ask for it, it's already allocated and set, and you don't have to worry about it. That's the general approach. I'm sure we've all done this hundreds of times, hopefully for less stupid examples than this one. All right, this is what it looks like at the Java level. Like, this is essentially what it compiles to. If we look at the decompiled bytecode, it looks exactly as we would expect it to. You've got the same thing going on with ints and integers, and it's doing the right thing there. OK, but there's a better way to do this with Kotlin. There's an automatic approach that takes exactly 1 line of code. Isn't that much better to use? Say, by lazy, we'll set it to 574. So it doesn't get set to anything until someone asks for it the first time, and then it goes through some operations to actually allocate and return this value of 574. And the question is, what operations does it go through? So I should explain first. Lazy is implemented using property delegates in Kotlin, and it's this generic mechanism they have for delegating logic somewhere else. So I want, when someone asks for this variable, I want you to run this logic over here and return other information from there. The other background piece of information is properties. Properties in Kotlin do much more than properties in the Java programming language, which means if you're going to access information on a property using reflection, well, how does that work through the bytecode since Java programming language doesn't have that capability? Right? Well, Kotlin needed to add capabilities so that when you use reflection, it will go through their extra or additional stuff to actually get that extra bit of information from their property. So they created this class called kProperty. And now if you use reflection on a Kotlin property, it can go through the kProperty and get that extra information that it needs. So that's the background. Here's what's going on inside of lazy. First of all, when you say by lazy, it automatically creates an array allocation. Brain should say, oh, there's an allocation. So you've got this kProperty array where it's going to set up the information for getting things from this Kotlin-specific property reflection mechanism that they have. So we've got the array, and the array consists of one item, which is this kProperty that they've set up specifically for this lazy property that you've told it about. You've got the class name, you've got the type, and that's basically it. You've got the name of the thing, right? So it sets us up array plus an allocation of the kProperty inside of it. Then it sets up this call internally. This is sort of initialization time code. It says, OK, there's this lazy thing that's going to return a class of type lazy. And from that, we can get the value. So when you call the getter on that property, it's going to call into this code, which is going to call a get value on that lazy object. And then it's going to call int value on that. All of this could bottom out in reflection code to go get it from kProperty, which is like even worse than the allocations we've seen so far. Like at the end of all of this, you may end up in reflection code just to get an integer value. However, because of extension methods, they're more clever than that, and they actually spit out this extension method that says, oh, if it's a lazy thing, if they're using the lazy class, then we're just going to call this function instead. So no need for reflection, even though kProperty stuff was set up and has reflection capabilities, we're not using that aspect of it. Instead, it'll just call into this method and get the value, which is this. Simpler than reflection, however, a couple of conditions to check, and a synchronized block in there just to get this int value from this very stupid example I've written. In addition to that, when all of this is set up, we go through initialization code, which in bytecode looks something like this. So basically, whenever you get into this and initialize this object, this is what gets emitted on your behalf under the hood, just to save an allocation of an integer object. As I said, stupid example, but real example is people doing it for small data structures like rep. So lazy is awesome. It's really cool that you can do this in one line of code. And if you have a complicated data structure or a lot of complicated object when it gets set up, and if it's not going to be used very often, totally worth considering. For avoiding the allocation of a simple int, probably not.
So now let's take a look at unsigned numbers. So this is a new experimental feature that was introduced in Kotlin 1.3. So Java has mostly signed numbers. And Kotlin is finally bringing unsigned numbers, which can be very useful when you do graphics code. For instance, when you have a width and a height, you want them to be unsigned. It's very useful as, as a type check that you're not going to get a negative value, which would make no sense for a dimension. So if you enable this experimental feature, here's how you can use the unsigned numbers. You can use the U suffix to declare a type to be unsigned. And under the hood, they're implemented using another experimental feature called inline classes. And we're going to take a closer look at inline classes in a little bit. But first, let's take a look at this example. So I declare 2 unsigned numbers, and then I just add them. So what happens? So every unsigned number is just an integer that's pushed on the stack and stored in a variable. So here, there's nothing interesting to see. And when we add them, we just load those 2 variables. We call the iadd operation opcode in bytecode, which is just the addition of 2 integers, which are normally signed. But JetBrains, they were very clever, and they realized that because of the way that signed numbers and signed integers are encoded, it actually works with unsigned as well. So they didn't have to create anything new. We can just use the existing bytecode. Everything happens at the language level. The only thing that's a little bizarre here is that we invoke a static function called uint.constructor-impl. And you can see that it takes an integer and returns an integer. So if we look at this particular function to see what it does, that's where things get a little surprising. And I'm sure the JetBrains folks would know why it does this. I have no idea. So we have this function, takes an integer, returns an integer, and here's the implementation. It loads the parameter that you give it, and then it returns it. And that's it. So I don't know why it's there. It's maybe for the debugger, so you can break on it. But other than that, I know that the JIT or the ahead-of-time compiler will get rid of it, or probably R8, so you don't need to worry about this. It's just a little strange that we have this extra bytecode for no reason. So if we look at the other operators, we saw that the addition is just implemented with the existing opcode add, same thing for the subtraction, same thing with the multiplication. It's only when you do a division that Kotlin has to invoke a special static method because the division works differently. So there's more code that runs here. So most of the time, unsigned numbers are basically free. So you should feel free to use them. Now let's look at what happens when you try to print one of those numbers, basically when you try to call toString on it. So here I have a signed number and an unsigned number, and I print them both. So first, let's look at the signed number. So we have this variable called z, it's equal to 42, and we call println on it. So that's exactly what we expect. But when we use the unsigned number, instead of printing it directly, because the default println in the runtime does not know about unsigned numbers, we have to go through something else. And because the unsigned numbers are implemented using inline classes, we have to box. So we call this function called box-impl. It takes our unsigned integers and wrap it into an instance of a class called uint. And that gets passed to println because uint has a toString method that's implemented and does the right thing. So even if you use unsigned numbers and they are most of the time free, you can end up doing boxing and therefore allocation fairly easily if you just add them to a string, for instance.
Let's talk about ranges. One of the curious things that a lot of programmers hit when they see Kotlin for the first time is the for loops. They kind of look for the syntax that they always knew from Java or C or C++ or other languages. And it's not that. Instead, all of the for loops work with ranges. And there are many ways to do this. So you could say for I in this range of 0 to 10 inclusive or exclusive until you get to 10. Or you could just say repeat the following operation, give it the lambda there. Or you could put the range on the front. These all look the same to me, modulo that off by 1 error that we have in the second one, right? So it turns out they're kind of different under the hood. So that first one works the way that we would think. It's basically the equivalent of the for loop we would expect in Java. Second one, same thing, except we're not going all the way to the last value there. Same thing for the third, like all straightforward iterations. But the way the last one is implemented is a little different. Instead, we're going to create an iterable object, we're going to create an int range object, and then we're going to use the iteration mechanism, which seems a little bit heavyweight for just having flipped the range to the front there. Not a big deal, but kind of curious that they're all quite different under the hood.
Yes, so in a traditional for loop with other languages, you can easily increment the counter by more than one. Instead of doing plus plus, you can say plus equal to. And the way you do this in Kotlin is you can use the step operator or infix function. So in that case, if we wanted to go from 0 to 10 inclusive, and we wanted to increment by 2, we would say step 2. And I would expect the code to look exactly the same as before, but we get this instead. So just by adding step, an optimization in the compiler basically disappears. And instead, we have to create a range. We have to create this in progression. And then the compiler calls get first, get last, and get step, which are, in this particular case, constants. So it's not entirely necessary. And then we have a while loop that makes sure that we iterate the right number of times. And it also happens if you say step 1. Which makes no sense to me, but I assume it's a missing optimization in the compiler.
That first step is a doozy.
Right. So inline classes, I touched on those a little bit when I talked about unsigned numbers. So inline classes are a way to wrap a type, one field, effectively. And the point of inline classes, as the name suggests, is that they disappear at compile time. We saw that with unsigned numbers. They're a class called uint. But really, when you look at the bytecode, all you see in the end is just an integer. So here I created my own inline class called color. And it wraps an integer because colors are often defined as an integer on Android. And I've created custom properties to be able to extract the red, green, blue, and alpha channels from the int without having to do that dance myself every time. So now, if we try to use that inline class ourselves, I created a print function that just formats a string using the different channels of the color. And I create an instance at the bottom in my main function. I call the print color function I just declared. And here's what the bytecode looks like in the main function. So first, we push a constant on the stack. It's that weird long number that corresponds to the hexadecimal value that you saw in the code. And then we invoke that color.constructor-impl function. And you can see its signature. It takes an int, which is expected because we wrap an integer, and it returns an integer. So it's exactly what was happening with unsigned before. We saw that this constructor actually doesn't do anything, just takes the input and just returns it directly. So there's nothing to see here. What's interesting is what happened to my print color function. So in my source code, it takes a color instance. But you can see here now it's called print color dash some weird name. It's probably a hash of something. Instead of taking an instance of color, it takes an integer directly. So the compiler rewrote the function to work directly on the primitive type I was wrapping. That said, sometimes inline classes are not free. We saw that with toString earlier. And the same thing can happen with the equal operator. So here I create two instances of my color class. And I just called, I want to print whether or not they are equal. And I do it in two different ways. First, we use equal, and then we do dot equals. And those should be equivalent. They should be the same thing. However, when we look at the bytecode, here's what happens. So when I do a equals b, first we load one of the variables. I think it's b. Then we call box-impl. And you can see that we're generating a color instance from that integer. Then we do the same thing again for the a variable, and then finally we invoke a static function called r=. That's part of that's an intrinsic in the Kotlin standard library. So just to be able to compare our two integers that we know are there, because we saw that the compiler sometimes is smart enough to get rid of the class, we just boxed it back into actual objects. We created two allocations just to be able to compare those two integer values. If you call a.equals b, things are a little different. We load one of the variables, and we box the other one. So instead of having two allocations, we have only one allocation. And instead here, we're calling a method called equals-impl on the color class. And you can see it takes an integer and an object. So if you're going to use inline classes, and you don't care about nullability, in that particular instance, you're going to allocate half as many objects if you say a.equals b instead of a=b.
Take a quick look at arrays. The implementation depends very much on little subtle differences in how you declare things. So here we're going to call int array of, and we pass in these things. And it's going to say, yep, here's a primitive array that contains those things. Or we could say array of, and we're going to pass these things, and we know that Kotlin is really good at type inference, and these are obviously ints, and it says, yep, here's your integer array. Or we could say, give me an int array, and actually ask for this thing specifically, and then it does the right thing with a little bit more code. We're basically initializing it inside the Lambda there, and it creates the primitive int array to whip through that.
All right, so with Lambdas, there's one particular use case that can be a little tricky. And we just recorded a podcast this morning with the Pocket Casts folks, and Tor mentioned that.
You just leaked that.
Yeah.
Uh-oh.
So what you're going to see is a possible programming mistake. Thankfully, we have a lint check in Android Studio that warns you against it. So here's, for instance, a class written in the Java programming language. It's a widget of some kind. And you can register listeners. So we have this interface. It has a single abstract method. It's a SAM. You can add a listener. You can remove the listener. And you can ask how many listeners are registered. Now let's try to use this from Kotlin. So first of all, we instantiate our widget. Then I create my listener as a Lambda. And it follows the, if we go back, our single abstract method takes a widget instance as a parameter. So we create a Lambda that matches this signature. It takes a widget, and then we do something with it. We print it. Then I call add listener on my widget, and I print the number of listeners that are registered. And finally, I try to remove that listener, and I print the number of listeners that are registered. What's going to happen is, So what's going to happen is that when we print the number of listeners after adding it, it's going to say there's one listener. That's completely expected. But after calling remove, the number of listeners is still 1. The remove did not work. And to understand why it doesn't work, we have to look at the code that's generated by the compiler. So here's what it looks like. We create our listener, because it's a Lambda, it becomes a function1 type internally. And a function1 is effectively a Lambda that has 1 parameter. But because that type is function1, it is not the listener type that our widget expects. So the compiler generates this extra class called widget_listener that is of the type listener that we expect, and it passes it our function1, our Lambda, so it wraps it into something else. And it's that other object that gets passed to add listener. And you can probably guess what's coming up next. When we call remove listener with our Lambda, it gets wrapped again, but it's a different instance. So we're trying to remove a different listener, and so we actually leaked our listener. And this is the kind of stuff that Android Studio will warn you against. The fix is fairly easy. You just have to be specific about the type of your Lambda. Just say it is a widget.listener, and don't just use the naked Lambda form.
So let's take a look at how extension functions actually work under the hood. So you have this simple class that I've defined. Again, I wrote this code all by myself. We have a superclass, and then we have a subclass, which extends that superclass. Awesome. Then we have a couple of extension methods that we've defined, one on the superclass, one on the subclass, and they print out this value, or they return this string value that indicates which one was actually called. So the super instance, we say, yep, give me one of those superclass objects. Subclass, give me one of those subclass objects. And then we have one where it is a subclass, but we cast it to a superclass. And then the question is, what happens when we call getIdentifier on each of these things? And then we have one more example where instead of pre-casting it, we're casting it at runtime to a superclass. So the question is, when we call getIdentifier on the superval, we get... Anybody awake? There we go. What a super answer. All right, how about the next one? All right, thank you. And number 3? Wrong. Sorry, super. So this is the one that's a little bit surprising, and finally the last one is the same. So it is a subclass. What is actually going on? Like, shouldn't it be calling that method on the subclass? It's because of these, the implementation of these things. So if we look at the decompiled bytecode, this is what we've got. GetIdentifier is now a static method, and it takes an instance of superclass. Same thing for sub, the getIdentifier on the subclass object. So that means that when we call it with a superclass object, we end up in the one that takes a superclass type. Same thing for sub, and same thing for sub cast as super. We have told the type system this is a superclass, no matter how we actually created it, so it's going to call the getIdentifier that takes a superclass instead. And same thing for the thing that's cast at runtime.
Default parameters, it's a very handy function in Kotlin. You can specify a default value for your parameters, and then you can use either name parameters to invoke them, or just omit the parameters and rely on the compiler to do the right thing. So here I have a very useful method. It takes 2 floats, and it just adds them and returns the results. Chet, where did the rest of the... Oh, sorry. Wrong slide. All right, so here's the code that gets generated. So from that code that we have that takes default parameter values, we have a new static function that was created that just takes our 2 floats without default values because we generated bytecode, and it just adds them and returns the result. But there's another method that was created. So it takes 2 floats, as we expect, and then it also takes an integer and an object. As far as I can tell, the object is always set to null, so I'm not sure why it's there. It's probably to tag those methods in a way or another. I should ask JetBrains. They will probably know the answer. And the integer is actually a bit field where every bit tells the method which parameters you did not specify at the call site. So you can see here when we check the first bit, var2 and 1, if it's set, that means that we did not specify a value, so we use the default value that we specified on the Kotlin side. And then we do this for every parameter, and at the end we invoke the actual function that's at the top. What's interesting, because it's an integer, I was wondering, there's only 32 bits, so what happens when you have 33 parameters? And we're going to take a look at that in a moment, but just here are some examples of how it works. So if I called my function directly without specifying any values, the Kotlin compiler would just use the default value 0, and then for the bit field, it will set 3, so the bit 1 and 2 are set, and it's going to use the default values. If I specify the first parameter, we see our value as the first parameter, which is 0 for the second one. The bit field is set to 2 because the second parameter is not set. Same thing when you specify only the second parameter. And then, of course, if you specify the 2 parameters, we call directly the function that does the actual work, and we skip all those checks. So we have only 32 bits. What happened? We will create a function that has 33 parameters. You should probably not do that in your code, but just in case, I double check for you what happened. Honestly, I was expecting the compiler to just say, nope, too many parameters, I can't do that. What it does, it creates 2 integers, so it just adds a second bit field, and it's going to look at the bits in both bit fields.
Because what's better than a bit field? 2-bit fields.
All right, finally, coroutines. We only have 3 minutes left, so we're going to go through this very quickly. How many of you use coroutines? OK, so sorry for those of you who don't know how coroutines work, but I'm not going to explain that too much. But basically, so you have a suspend function. That means you can do heavy work in there. And here I call a function called delay. We're simulating heavy work. Then I launch a coroutine. So we print that I'm launching a coroutine. Then I call launch. I call my suspend function twice, so compute and compute. And finally, I print exiting coroutine. So if we run this program, we're going to see the following output. We're launching the coroutine. We're computing, that's our suspend function. We're computing again, that's our suspend function, we exit. Coroutines are implemented using state machines. So if you look at the code that's generated, it's going to look something like this. There's going to be an invoke suspend function generated somewhere. And at the top, it does a switch on an internal field, so that function is inside the class. And it switches on the field called label. And label is basically where you are in the coroutine state machine. So every suspend function you call in the coroutine will be a state in a state machine. So here you can see we switch on label, and in the case 0, we set the label to 1. That means we advance to the next state. And we call our first instance of the compute function. When those suspend functions return a magic value called suspended, we return from the state machine. That means that the coroutine has to be paused, and we'll have to come back later when we can resume execution. And again, if you look at the other state, so when the state is 1, we advance the state to 2. We call compute a second time, and we return if we're suspended. So what I did is I took the bytecode of that, and the bytecode starts like this, and I hacked it to add this. You don't need to understand what it's doing, but basically all I wanted to do was print the current state of the coroutine, of the state machine, and rerun the program to see what's going on. So this was the original output, and when I print this label field, this is what it looks like. So we launch the coroutine, we enter that state machine, the state is 0, we call compute, our first suspend function, we return because we're suspended, and then at some point later, we re-enter the state machine. Now the state is 1, we invoke compute, we return again, we come back into the state machine with the last state, and then finally we exit the coroutine. So again, you should not worry about this too much in your code. You use coroutines, they're amazing. It's just very interesting to go look at the bytecode, at the generated code, to better understand how they work, what looks magical, how it works under the hood. And with that, you have 30 seconds, Chet, so go
Excellent.
fast.
Wrap up. So the question is, should you actually care about this stuff? We've given a couple of talks in the last couple of years that said, you know what, the runtime has gotten so much better. Stop worrying about all the allocation and deallocation stuff. We told you early days of Android, avoid allocations. Now, no, do the right thing for your code and your APIs. So the question is, did we lie to you? And the answer is no. Actually, we were telling the truth. That is still good advice. However, oh, yeah, and there's the advice. Yep, allocation collection is always fine. But it's good to actually understand what's going on in the hood. If you are trying to be lazy about allocating even a rect object, that's not the right approach, right? It probably doesn't matter, but isn't it nice to actually know what's going on? And especially if you're in an inner loop somewhere, maybe you actually don't want that overhead. Maybe it doesn't matter. On the other hand, if you can save it in a case where it actually matters in an inner loop, that's probably a good thing. And that is it. Thank you.